who isolates something from the soil bacteria or from a sea squirt or something like that, and is starting really from scratch. And so for most of our examples in here, you're going to have some kind of idea of what you started with, and so you're going to know some of the parts of the molecule, but you're not necessarily going to know what the end goal was. Of course, all the rules are the same, right? All the 1D and 2D NMR experiments that you would use to assign a natural product are the same as you would use to assign your unknown product. But because we don't really have any natural product chemists in here, I don't really give you completely blank problems. And so the way that I want you to approach all of your NMR problems, not just in the course, but in your real life, is to sort of ask these questions first. You know, if you set up a reaction in the lab and you got a product, did you make what you wanted or what you expected? Figure out what properties the spectra would likely have for that candidate molecule, and decide whether or not your spectra is consistent with that or not. And if not, what did you make? And so the way that I want you to be approaching these problems is in an iterative sense, to come up with some kind of candidate structure. Think, what would the spectral properties associated with that candidate structure likely be? Figure out whether or not that's what you're seeing in your spectra, whether that's consistent or inconsistent with your candidate structure. And then go back, what do the spectra imply about your molecule? How can you revise your candidate structure? And then repeat that process, okay? There are a lot of tools that we can bring to bear on solving structures. Most important, certainly to organic molecules, but to many organometallic structures as well, are proton and carbon NMR. And so we're going to be working through where chemical shift comes from and what kind of information you can extract from the chemical shift for both proton and carbon NMR. We're going to talk a lot about peak patterns, peak shapes, which it turns out are often a lot more useful in terms of assigning structures. We'll talk about coupling constants. We'll talk about coupling also a little bit in terms of carbon NMR. Coupling doesn't just happen in protons. And we'll talk about some other 1D spectra that we can do in carbon, like DOUBT, NMR, and other such things. We'll kind of move into the 2D world. We'll talk about COSY spectra, NOESY, HSQC, HFBC, and a few other things. Give you a little bit of primer about infrared, and won't really talk so much about mass spec because that's covered in another module. Okay, makes sense? Okay. So let's start with a little bit of background on NMR. I don't want this course to get weighted down in theory, but it's helpful, I think, if you've got a little bit of an idea of where some of these terms like parts per million and where upfield and downfield kind of come from, and why we use those particular words when we're talking about NMR spectra. So the first thing that we need to know about is this property of some nuclei